When you look at a busy street, your brain instantly maps the chaos. You identify cars, pedestrians, and traffic lights in milliseconds without trying. But a computer sees a massive, flat grid of numbers, where each value simply records the brightness of a single pixel. These raw numbers are incredibly fragile. If a cloud passes overhead and changes the lighting, or if the camera shifts just a few inches, every single value in that grid changes. For a machine, the image has been completely replaced. To achieve reliable classification across different environments, the system must move beyond the raw pixel values. Instead, the algorithm extracts features. These are robust visual descriptors, like sharp edges or specific textures, that remain mathematically stable even when the lighting or the camera angle shifts. Effective machine vision relies on isolating these persistent geometric patterns, allowing the system to maintain its focus on the object despite the surrounding environmental noise. In the early days of computer vision, engineers acted as translators. Humans manually wrote strict mathematical equations, telling the computer exactly which visual clues it needed to look for. We call these handcrafted features. This image shows the result of a Sobel operator, a specific mathematical filter designed by humans to isolate vertical and horizontal edges, outlining the face and the bookshelf in stark white. But human-designed rules hit a wall. The real world is messy. A static equation written in a lab is too rigid to account for every possible shadow, angle, or occlusion a camera might encounter. The solution was the convolutional neural network, or CNN. Instead of humans writing the strict rules for what a feature should look like, we feed the network raw data and let the system discover the most effective mathematical descriptors on its own. By doing this, artificial intelligence shifted from a rigid instruction follower into an autonomous engine capable of discovering its own mathematical logic. A CNN begins by zooming in on a tiny receptive field, scanning the lower 12 by 12 grid. Inside, it performs a convolution, multiplying pixel values by kernel weights and adding them together. This collapses the window into a single value, building a completely new, filtered layer. This diagram outlines the broader architecture. Those newly generated grids are feature maps, large blue panels following the input. They highlight specific geometric patterns over raw light. This process loops continuously. The feature maps are subsampled, shrunk down, and fed directly into the next layer. By stacking these processing layers, the network builds complexity. The first layer might only detect simple edges. The next layer combines those edges into curves. By the deepest layers, it can recognize specific shapes, like a bicycle wheel or a dog's ear. The deep neural network distills the image layer by layer, mathematically filtering out irrelevant data until the structural identity of the object becomes the dominant data point. Once the deepest feature maps are formed, they are flattened into a single, dense list of numbers called an n-dimensional feature vector. This mathematical summary is passed into a mechanism known as the classifier, making a definitive decision on what the image actually contains. Inside this classifier, algorithms like the perceptron draw a strict boundary. This animated plot shows exactly how it works. It evaluates the weights of the inputted features and draws a rigid, linear line to separate one class of objects from another. The algorithm identifies where to draw this line through repetition. It processes hundreds of thousands of labeled training samples, making countless mistakes until it finds the alignment that best separates the data. Every time the classifier makes a wrong prediction, a feedback loop kicks in. It quantifies the error and sends that information flowing backward through the entire system, a process called backpropagation, to slightly tweak the kernel weights in the earlier convolution layers. Modern AI operates by building a self-correcting mathematical landscape, an evolving architecture built to decode the visual world through pure geometry and statistical boundaries.